Now we have our first example in the specific heat section. We have example 1, you have 100 newtons, you're applying 100 Newton force downward 40 degrees on a 2 kilogram block of ice. The coefficient of kinetic friction is 0.4. The initial temperature of the ice block is -1 Celsius. It says you drag a block of ice with a temperature of -1 Celsius and mass of 2 kilograms across the floor for 30 meters. So you're pushing on this block of ice downward, right, for a distance of 30 meters. And then because there's friction, the coefficient of friction is 0.4, the friction is doing work on the ice. And that work done by friction goes into heating the ice, right? And it also goes into heating the surface, the floor that it's on. And it also goes into heating the air a little bit, right? So it goes into different sources. So now it says assume 80% of the work done by friction goes into heating and melting the ice. How much of the ice melts, right? So maybe a portion of that ice will melt. Let's see how much of that ice will melt. So let's do a little bit of physics 1 kind of analysis on this, right? Draw the free body diagram. So I've got the weight of the object, 2 times 9.8, which is equal to 19.6, right? And then I've got the downward force. I can write it this way, 100 newtons, right? And then this is equal to 40 degrees. Right? Since it's 40 degrees this way from the horizontal axis, we can also write it this way, 40 degrees below the horizontal axis, right? Then we got the normal force of the ground supporting the block. So we can break the force, your force into horizontal component, 100 cosine of 40, and then the downward component, 100 sine of 40, right? So then what's going to happen? The downward component of your force, the 100 sine of 40, is going to cause the normal force on the block to go up, right? Because you're pushing down on the block, it's going to make the block feel heavier, right? So we can say N minus 100 sine of 40 minus the weight of the object, 19.6, is equal to 0, right? So in the vertical direction, since there's no acceleration, all the forces must add up to 0. So using this equation, we can calculate for the normal force. N is equal to 100 sine of 40 plus 19.6, right? So let's calculate that. So now, the work done by friction is going to equal to the force of friction. Is going to equal negative, so 0.4, right? And then the normal force is 83.879, and then the distance was 30 meters, right? So then we can multiply all of that. So done by friction is equal to 1006.5 joules. So it does a lot of work, right? So it's negative. But that negative means that the friction is eating away from the energy of the system. And then where's that energy going? It's going into heating the surface, the ice, and also the air, right? So now let's say 80% of that energy now goes into the ice alone, right? So 80% of that energy, 0.8 of the work of friction. So right now we don't care about the negative, just take its absolute value. So 0.8 times 1006.548, so times 0.8. So that's equal to 805.2384 joules. Heat is equal to what? Well, since the ice starts at -1 Celsius, we're going to have to heat that ice up to 0 Celsius before we can even start melting it, right? So we're going to say the mass of the ice times the specific heat of the ice times change in temperature of the ice plus the mass of the ice that it melts. So this is the total mass of the ice, right? Plus what portion of the mass of the ice that actually melts. So this is mass ice melts times LF. And LF is the heat of fusion of ice, right? So we put here 805.2384. The mass of the ice total is equal to 2 kilograms. Now what was the specific heat of ice? Okay, so we can get that from our table that we wrote down before. The specific heat of ice was 2090 joules per kilogram Celsius, right? So I'm using the joules per kilogram. Now, since this mass was given in kilogram, the kilogram and the kilogram will cancel, right? The change in temperature is going to be what? Well, 1 Celsius, because you're going to go from -1 all the way to 0 Celsius. So the change in temperature is 1. So that's 1 Celsius. So the Celsius will cancel the Celsius. And then this is joules, right? And then that will cancel the joules because 805.23484 is in joules. So the joules will cancel the joules. That means the units will work out so that the units on the left and the units on the right are the same, right? So then on top of that, I have to add mass of the ice that melts, which I don't know what that is, right? And then let's put down the heat of fusion of ice, which was what? 3.33 times 10 to the 5th joules per kilogram, right? And then of course this joules will cancel that joule, and then that joule will cancel. So the answer that we get when we calculate this, the mass of the ice that melts, will come out to be in kilogram, right? So then I'm going to do this. Take 805. So what actually ends up happening is that 2 times 2090 is 4,000, and it's actually larger than this. So that means that none of the ice actually melts, right? So in this kind of a problem where you don't know whether the ice melts or not, this is the way to find out. This number ended up being larger than this. So what does that mean? The ice never actually melted. So let's find out, and therefore, what the final temperature of the ice is, right? Its temperature went up a little bit, but we don't know how much. So this one, we're not going to be able to calculate. So then we have here 805.2384, and then we can put here the mass, which is 2 kilogram, times 2090, and then we'll put delta T, but the delta T, we're going to solve for what delta T is, right? So then we're going to divide 805, right? So if the temperature original was -1, and we add this to that, so -1 plus the answer, so the final temperature is going to go up slightly, all the way from -1 to -0.807. So that's all that's going to happen. It's not really going to melt. Now, what would have happened if the initial temperature was different? Let's say the initial temperature was -0.1 Celsius. -0.1 Celsius. So that means the temperature wouldn't have to change too much before the ice actually starts melting. Well, then the conditions might be different, and the ice might actually go up to 0, and some of it might actually melt. So how would the answer change? Well, this 805 would still stay the same, right? 2 times 2090, and then we would put here 0.1 Celsius. 0.1 Celsius, right? So the temperature would only have to rise by 0.1 before it actually starts melting, and then we can still have M ice melts 3.33 times 10 to the 5th, right? So then what would the answer be? Then we would have here 805.2384, and then we would have 2 times 2090, 2 times 2090 times 0.1, and that would be 418, right? Plus, and then you would have mass ice melts, then you would have 3.33 times 10 to the 5th joules per kilogram, okay, and then the joules would cancel. So then you have here 8. What units will that come out to be? Since this is joules per kilogram, this will be M is equal to 1.16 times 10 to the minus 3 kilogram, right? So the answer is in units of kilogram, which means that since this is 10 to the minus 3 kilogram, this is actually gram. So mass of the ice melts is equal to 1.16 grams. So about 1 gram of the ice melts, not that much, 1.16 grams, okay? So depending on the conditions of the problem, how much mass of ice there is, how much you dragged the ice, how much force you have applied, the coefficient of friction, and then its initial temperature, the answer might vary, right? Some of it might melt, none of it might melt, so it all depends, okay? So now you can see how to do this kind of problem. Thank you very much.